All right, here in chapter 9, we will be investigating the second of our inference general procedures called significance testing or hypothesis testing. Um, we will be looking at this chapter will be broken up into 3 sections, just like the previous chapters were. So the first section 9.1, which we're starting here, is talking about the basics of significance testing. So it doesn't really go into the mechanics or formulas for calculating the probabilities that we're going to be interested in, but instead it's just talking about the basics ideas of it. And then in 9.2, we'll get into how we apply those to proportions. And then in 9.3, we'll get into using them for means. There will be a significant difference in how we do them with means, so much so that we will have a new table to look at. So the sampling distribution will have a slightly different shape than the normal distribution, but we'll get into that when we get to section 9.3. Okay, so significance testing then. So last chapter we talked about confidence intervals, and that is one of 2 really important inference procedures, and we use that for estimating what a population parameter would be from the data sample. So we would either approximate it the population mean or the population proportion from the sample data. And here, and of course, we couldn't calculate it exactly. We came up with a confidence interval and that kind of thing. Well, here, what we do, instead of trying to estimate a value, we have a hypothesized value, and then we're going to test whether the data supports that. So we'll be looking at a sampling distribution and thinking about probabilities again. So it's a lot like what we were doing in chapter 7, but except now instead of just calling it what's the probability that would be this far or further into the tail of our distribution, now we'll kind of formalize that. Okay, so significance test is a formal procedure for comparing observed data with a particular claim, and that claim we refer to as the hypothesis. So kind of like if you're doing in science, you have like a hypothesis that you're trying to test with an experiment. Same kind of thing. We have a particular thing that we think is true. Either we think a population parameter is true, and then we take sample and we look at the sample statistic and we say, okay, how likely is it that we would get a value as extreme or more extreme than the one we got if that hypothesized parameter value is actually true? All right, and again, we will be using here. We'll be using proportions. We'll be trying to look at a statement about a population proportion or a population mean value. All right, so if you look at the electronic version of this PDF, I made this part of the screen clickable. So if you click on it, it will take you to this Applet website that is testing the claim that a friend of yours is an 80% free throw shooter on the basketball court. And so this applet works through that. And so we'll open that up and play around a little bit with that and see sort of visually, what's the probability that we would get the results that we got if he really is an 80% free throw shooter. All right, so this little applet that comes along with our textbook, and I will also set up a link in your PDF so that you can access this if you want. So this is, you go and you're on the court and you have a friend who tends to brag a little bit, and they claim that they are an 80% free throw shooter. And so you say, okay, well, let's have you shoot 10 baskets and let's see how many of those baskets you make. So this is what we're going to do. I'm going to go ahead and hit the shooter. You can see the line up here is at 80%. So that's where we would expect the shots to go. Let me just do one shot at a time to start with, so that way you can kind of get a sense for what's going on here. So he shoots one basket. Okay, he missed it. He shoots another basket. Okay, he makes it. So right now, this graph is at 50. That means they've made 50% of their baskets, right? All right, so let's have him shoot again. That's the third shot and fourth shot. All right, so after 5 shots, he has only made 40% of his baskets. Okay, so then let's have him shoot some more. Let's do 5 more. All right, so you can see out of 10, he's only shot 4. So that kind of makes me feel like maybe he's not an 80% free throw shooter. Or maybe he just hasn't, tried enough, right? In other words, maybe he just got kind of unlucky on these first couple, right? We expect every sample to have some kind of variability. And so we would probably want him to shoot more, right? So like a larger sample is going to be more representative of the true population. So in this case, the parameter that we're trying to estimate is the population proportion, the true proportion of free throws that he's able to make. And so we would probably want him to try more than 10. So okay, maybe he just got a couple of really bad shots in there, right? I mean, we're talking about this as random. If he really is an 80% free throw shooter, how likely is he to only make 4 out of 10, right? So that's what we sort of have to think about. And this whole chapter is about looking at and calculating the probability that this would happen based on, if he is a true free throw shooter of 80%, what's the probability that he would only make 4 out of 10 shots? And of course, that's 40%. So let's do 10 more shots. So now you're probably thinking okay, yeah, he's still at 40%. So it's now looking less likely, right? So the more shots he makes and actually misses, I mean, he attempts and misses, and he's still at 40%, the more likely he's probably not an 80% free throw shooter. Now, this, in reality, we would never know what his true free throw shooting rate is, what his true proportion is. But here we can click on this little button up here and it'll show what his true proportion is. So in this case, yeah, he really was 40% free throw shooter. And just as we would expect, it's kind of zeroing in on that. So let's take this up to 100 and let him shoot 100. Now that might take a little while, but you can see now as this goes out, it's zeroing in. Well, actually, he's getting a pretty long string of bad luck there. But as we continue, his sample proportion is getting closer and closer to his true population proportion. But there's some variability. You can see he's up and down a little bit. And let's see, we've got, looks like we're getting to about 120 here. But you can see how his true proportion of 40, we're zeroing in on that. We're at 39% right now. So that's what we would expect. And now after we've done 120, even if we don't have the true one showing, after 120, he's at 39%, probably not very likely that he's a true 80% free throw shooter. All right, let's do another one. Okay, this time he's starting out pretty high, and looks like after, we're doing 100 again. Even after 30, he's still up near 80, so it's looking like he probably is an 80% free throw shooter. Now, in reality, we're not going to have him, probably throw 100 a sample size of 100, we'll do something less. Let me get our sample size back down to something that's not obnoxiously long. So let's say 10. So we got a new shooter again. So now we have a new probability, a new true probability. Now he claims to be 80, and so that's why that blue line is still there. Let's have him shoot 10 shots. Okay, so after 10 shots, he's at 90%. All right, so maybe he's not an 80% free throw shooter. Maybe he's actually 90%. Let's do another 10. All right, so he's still at 90%. So, in this case, it's looking like probably he's 90%. Like, what's the probability that he would shoot 90% of his free throws in his sample of 20 if his true proportion is actually 80%? All right, so that's kind of what we're looking at, is what's the probability that this would happen, or something more extreme. And that's really what we're checking. We're testing the truth that he's truly an 80% free throw shooter. All right. Okay. So significance tests is, first of all, we're going to come up with, we're going to start with some kind of statement, some kind of claim, and that we want to sort of test whether or not that statement is true or not. And so that statement will be what we call the null hypothesis. Sometimes we'll refer to it as H naught. So it's an H with a subscript 0. Old English word not just means 0 or nothing. So we will claim, we will want to look at the evidence to support or refute the null hypothesis. All right. And then the alternative hypothesis is what we think is going to happen. So we have to, before we even look at data, we're going to have to look and say, well, our friend thinks he's a free throw shooter of 80%, but we know he's a braggart. And so maybe we're like, okay, we think it's less. And so the null hypothesis would be that he's an 80% free throw shooter. The alternative is what we suspect is really happening. And so in our case, if we think he's a braggart, then we would say, well, we think it's less than 80%. So we can never claim like, oh, we think he's really 40%. All we state is that we don't think he's 80, or in this case, we think he's less than 80%. So the null hypothesis will be that he is 80. That's kind of what he's claiming. And then we think he's actually worse than that. So we would say that the alternative hypothesis is that P is less than 80%. Okay, where P is the proportion of free throws. All right, so the null hypothesis is always given as the parameter, the population parameter is equal to some value. So you always have to include some equal sign there. The alternative is often going to be, oh, well, we think it's less, or we think it's more. If we don't have an indication of which direction, then we'll use not equal to, right? So if we don't know this person who's throwing, we don't know if he's a braggart. Maybe he's very modest and he just says he's 80%. In reality, he's more. So if we don't have any inclination, then we'll just say not equal to if we don't have a direction of interest. All right. So if it's larger than or smaller than, if we say less than or greater than, then it's a one-sided test. So if you think about it, most often we are talking about a sampling distribution, and the value that we're testing that we get is down in one of the tails. So like when we did in chapter 7, we tested, what we looked at is what was the probability that we would get a value as extreme or more extreme than the one we got. So either greater than down up into the high tail or less than down in the low tail. So that's why we call these one-sided, because we're in one side of the tail or the other side of the tail of the normal curve. If we don't have a direction and we just say not equal to, then then we're going to reject the null hypothesis, the claim that he's 80% free thrower, if he were to score, if he were in his sample were to get a p hat that's much higher than 80 or much lower than 80, then we would reject it. So we're going to reject it based on being in either side of the tail. Either side of the either tail, high tail or low tail end of the normal curve. So that's why we call, when it's not equal to, we'll refer to it as two-sided, rather than just less than or greater than. One or the other would be one-sided test. Not equal to will be a two-sided test. All right, so a couple of rules to follow when you're coming up with your hypotheses. The hypotheses should express the hopes or our suspicions that we have before we look at the data. So it's you can't send your friend out and have him throw 20 baskets to see if he makes them, right? Attempt 20 shots and then decide what your hypotheses would be. That would be cheating. You have to come up with what you think it is first, write your hypotheses, and then collect and analyze the data and see, then make a decision based on that data, whether to reject your null hypothesis or not. All right. Also, the hypotheses should be stated in terms of the population. In other words, if we have our friend shoot 10 baskets and he makes 60%, then we don't have to try to guess at what the p hat's going to be. We know the p hat is 60%. What we're interested in is what is his true proportion of free throws, not what is his sample proportion. We know what the sample proportion is, so we never state hypotheses based on statistics. It's always based on population parameters. So, for example, we would never say a p naught or H naught, or the null hypothesis is that p hat is equal to 0.64, because we know what the p hat is from the data, or we will once we collect the data. So we never make any kind of null or alternative hypotheses based on statistics. It's always on parameters. So don't do that. All right, so here's an example. This is actually, I think, one of our homework problems. A survey. The survey of study habits and attitudes is a test that measures the students' attitudes towards school and study habits. Scores range from 0 to 200. The mean score for U.S. college students is about 115. A professor suspects that older students have better attitudes towards school. So she gives the SSHA to a simple random sample of 45 of over 1,000 students at her college who are at least 30 years old. So she's specifically looking at a sample that are 30 years old or older, which is old for college students. So, next year when you guys go to college, you'll see that there are not very many old people in your class. Very rarely do you get anybody in their 30s in any of your classes. All right, so what would the null and alternative hypothesis be based on what this professor suspects? So you would want to use symbols. So we want to use population parameters. So we're either going to use population mean mu or population proportion p. So is this proportion data or is this mean data? Write down the the equations or inequalities in your two null and alternative hypothesis, and then say what that symbol means. All right, so our null hypothesis will be that there basically is no difference between older and younger students, right? Older students are not different than younger students. They have the same, right? That's the null hypothesis. So there is no difference. And so how does that look? That looks like, well, the mu for older students is the same as the mu for younger students. So the mu is going to be 115. The mean test score is 115. The alternative, this is basically what the professor suspects, right? The professor suspects that what? The older students will score better because they're older and wiser and they realize that school is a little bit more important. And so they would say that she would say that they would score higher. So that would be a mu is greater than 115. And then you have to say what the mu is, right? So the mu is not the population mean of all students. We know what the population mean of all students are. That was given to us, so it's 115. But what we don't know is what the mean population score is for older students. And so that's what our mu is. So here mu is the mean score, the SSHA score for all students that are older than 30 years old. So for the older students, that's what mu is, the average score for their test. Now, we're not analyzing this, and we're not coming up with how likely that is to happen, that kind of thing. Right now, we're just looking at setting this stuff up, setting up the null and alternative hypotheses correctly. All right, let's try number 2. Hemoglobin is a protein in red blood cells that carries oxygen from the lungs to body tissues. People with less than 12 grams of hemoglobin per deciliter of blood are considered anemic. A public health official in Jordan suspects that Jordanian children are at risk of anemia. So he measures a random sample of 50 children, obviously Jordanian children, in Jordan. Okay. So set up your null and alternative hypothesis. Remember, the null hypothesis is always including an equal sign. And think about whether are we doing with proportions or if we're dealing with means here. Okay, so the mean is equal to 12, the population mean. And then what are the suspicions? The suspicions are that Jordanian children are more at risk. So that means that the mean blood hemoglobin concentration of hemoglobin in Jordanian children will be less than 12. So mu is less than 12 would be the alternative hypothesis, where mu is equal to what? So you have to state what the mu is in this case. And it is the true mean hemoglobin in Jordanian children. So not the 50 children, but all children. So you have to make sure that you're stating this as that you know the mu represents the population, not the 50 children. So it's not the X bar that we would get when we look at the blood data from the 50 children, but because we know what that is, we don't have to, we'll know whether that's under 12 or whether that's over 12. But it's the whole population that we don't know anything about. All right. So going back to our basketball example, suppose a basketball player claims to be an 80% free throw shooter. To test this claim, we have him attempt 50 free throws. And let's say that he makes 32 of them. His sample proportion would be 32 over 50, or 64%. All right, so what can we conclude about this from our sample data? So our sample data is that the p hat is 64%. He claims that his true proportion, is 80%. All right, so we could, for now, we're going to want to calculate the probability that we would get the result we got, or one more extreme. So this is a lot like what we were doing in Chapter 7 when we were doing the probability that we would be at this, that given the true proportion is 80%, how likely that would we have a p hat after 50 throws? We'd have a p hat of 64, or one more extreme than that, right? Or less, because that's below the mean. So we don't have yet the mechanics on how to do this. So what we're going to do is just say, okay, let's assume that he is an 80% free throw shooter. All right, then we have the software generate an approximate sampling distribution if this person who's actually an 80% free throw shooter, and we have them attempt 50 shots and we have them do it 400 times. What would that look like? And so this is what it would look like. Now, again, we run this several times and we'd get slightly different approximate sampling distributions, but you notice it's centered at the 80. Now, this is not, again, some people look at this graph and say, oh, that's proof that he's actually an 80% free throw shooter because his sampling distribution is centered at 80. But remember, this approximate sampling distribution is based on the truth of him being an 80% free throw shooter. So what we want to do is we want to say, okay, so if that's true, if he's actually an 80% free throw shooter, we would expect the sampling distribution to be very similar to this computer generated one based on that truth. And so how likely is it that we would get a result, or he would only make 64 or less % of his free throws? And you can see it's circled there. There are only 3 out of 400 attempts that were as low or lower than 64%. All right, so that's pretty low, right? So you can say how strong the evidence against the player's claim is by giving the probability that he would make as few or fewer than 64%, in this case 32 out of 50 attempts in the long run. And so that is less than 1%. So 0.75% chance that if he was really a free throw shooter of 80%, it's less than 1% chance that he would have done as badly or worse than he did in his attempt at 50 shots. All right, so the observed statistic, that's the p hat of 64%, is so unlikely. If the true parameter were actually 80%, then this is really sort of evidence that his claim is not true. It's very unlikely that he would have done as badly as he did or worse if he was really an 80% free throw shooter. All right, so there's 2 things that are possible here, 2 outcomes that could be happening. The null hypothesis, that is, that he's an 80% free throw shooter, is actually correct, and he just happened to have performed badly, right? That he just, by dumb luck, only made 64%. It happens 3 out of 400 times, so it's certainly possible, but just not very likely. So that's one possibility, that even though he did really badly in his sample, he really is an 80% free throw shooter, and it's just a very unlikely outcome is what happened. The other outcome, the other possibility is that the alternative hypothesis is actually correct, and that he actually does have a free throw shooting rate less than 80%. And that's what our sample statistic, our data from the sample sort of suggests. All right. Now, the whole basic idea is that if an outcome would rarely happen based on the truth of the null hypothesis, so if it's very unlikely to get the result he got or one more extreme when the null hypothesis is true. So if the probability that he would get 64% free throws or worse when the true proportion is 80%, then this is good evidence that the null hypothesis is true. Oh, sorry, it's not true. So a low probability is evidence against the null hypothesis, right? So the low probability is the probability that we would get a result or one more extreme when the null hypothesis is true. And so low probabilities, right, something that rarely happens when the null hypothesis is true, means that that is evidence against the null hypothesis, or strong evidence that the null hypothesis is not true. All right, so the null hypothesis states the claim that we're seeking evidence against. So the probability that measures the strength of that evidence against the null hypothesis is called the p-value. So this was the probability that we were calculating back in chapter 7. It's like, what's the probability that we would get a value as extreme or more extreme than the one we got, based now on the truth of the null hypothesis. All right, so that p-value is really just a probability. So it's a probability that the statistic would take on a value as extreme or more extreme. So further down into the tail, one way or the other, when the actual null hypothesis is actually true. All right, so this is what we call the p-value. It's really just another fancy name for the probability that we would be as extreme or more extreme than where we are if the null hypothesis is true. All right. So, for example, in our example here, this is not a true sampling distribution. This is a computer-generated approximate sampling distribution. We'll get into the mechanics in the later sections on how to calculate the true probability or true p-value. But based on this simulation, our p-value would be about 0.75% because the probability would be 3 out of 400 attempts. All right, so again, small p-values are evidence against the null hypothesis. So the probability of getting this value or one more extreme, if it is small, that's what the p-value is saying. If that is small, then that is evidence against the null hypothesis. Large p-values say that the probability of this happening is rather high, and so we would that large p-value would fail to give evidence against the null hypothesis. All right. All right. So the final step in performing the significance test is to draw a conclusion. And so we have to be careful how we state our conclusion. All right. We will make two decisions. All right. We either reject the null hypothesis or we fail to reject the null hypothesis. So it's almost like we want H, it almost feels sometimes like we want H not to be wrong, right? I mean, it's not, but that's kind of how the wording sounds. So we either are going to reject H not, or we're going to fail to reject it. Like, we don't have enough evidence to say it's wrong. It's almost as though we want it to be wrong. I mean, we don't, but that's what the wording kind of sounds like. All right, so we reject the null hypothesis or we fail to reject the null hypothesis. We never say anything that says like, oh, we accept the null hypothesis or that the null hypothesis is true. We do have, if the evidence is strong enough, we will say we reject the null hypothesis, but we don't ever say it's false or it's wrong. But we reject the null hypothesis or we fail to reject it. The only language that we use in this case. It's impossible for us to say that the null hypothesis is true or that the null hypothesis is false or that we accept the null hypothesis or anything like that. All right. So we just say reject or we fail to reject. So small p-values mean we reject the null hypothesis, and that says that we have convincing evidence for HA. We never say that H naught is false or that HA is true. We don't use those kinds of language. We don't say anything that makes it sound like we definitively know for sure that we did the right thing, because ultimately we could be making mistakes. And we'll talk about that in the next lesson. All right. So the other option is that p-value is large, which means we fail to reject the null hypothesis. And then we say we do not have convincing evidence of HA. All right, we never say anything that sort of makes it feel as though we're saying the null hypothesis is true or that it's correct or that we accept it. All right, not language what we use, because again, we just never really know that it's true. An analogy that we can use is that if you are accused of a crime, right, we say the accused is innocent until proven guilty. That would be sort of like the null hypothesis. The accused is innocent until proven guilty. All right. The defendant either committed the crime or did not. We never really know for sure, right? We don't really know for sure whether the person committed the crime or not. You and 11 of your peers can either say he's guilty, which means you reject the null hypothesis, you reject his innocence, or he's not guilty, in which case you failed to reject it, but it's not quite the same as saying he's innocent, right? We never say we accept the null hypothesis. We never say the accused is innocent. What we say instead is he's guilty or he's not guilty. We just don't have enough to prove that he's innocent, though, right? So he's not guilty or he's guilty. Be careful. We never accept H not. All right, so significance level now. So how small is small enough? In other words, if p-value is small, we're going to reject the null hypothesis. Okay, so how small does p-value have to be? So there's no set rule for how small it has to be. It depends on the situation. More often than not, we'll have a specific value that we will use. And usually, as we've seen in the past, that's about 5%. But sometimes it can vary. All right, but that threshold is called the significance level. And we use Greek letter alpha to denote that significance level. All right. So if the p-value is smaller than our alpha, then we say that the data is statistically significant at an alpha level of whatever the alpha level is, 0.05 or whatever. Okay. In that case, we would reject the null hypothesis, and we would say that we have evidence to support the alternative hypothesis. And we'll get into more details of these and how to say it as we get into the later sections. But your conclusion, we're going to get into our 4-step process here. And our conclusion will have 3 components. So first, you'll compare your p-value to your alpha. And then you'll either reject or fail to reject. And then you will say we either have convincing evidence or we do not have convincing evidence of HA, all based on your p-value. So if the p-value is small, lower than alpha, we reject it. We have convincing evidence of HA. If your p-value is greater than alpha, then we will fail to reject it. And we'll say we do not have convincing evidence of HA. Now, technically, if it's equal to alpha, we would fail to reject. So it has to be smaller than alpha for us to reject it. If it is equal to, then we will fail to reject. All right, so your homework is 1 through 19. Do next class.